Yes, the topic is really hot. Yes, the Hubble constant tension. So lots of research, on cosmology, on testing, the standard LCDM model. And I try to, convince you that, we are basically left empty-handed, in terms of, cosmological exploitation of, possibilities. So maybe it's really, we have to be really daring, to ask this question, is it really a true cosmological anomaly, or, there is some, very nasty systematic effects, hidden in the measurement. Yes, so that's the outline of my talk. I will start, with the Hubble constant tension, since I will try to convince you that the most likely, in my view, source of possible systematic errors, these are type-1A supernovae, how we model them, how we understand them. I'm going to spend some part of my talk on type-1A supernovae, standardization model, understanding something that is called supernova color correction. It's going to be very relevant. Then a little bit about some more sophisticated models, two population hierarchical models, and then I will come back to systematic effects in the local measurements of the Hubble constant. Okay, so the Hubble constant, this is basically a coefficient of the linear relation between escape velocity and distance. That's a historic plot from Hubble. That's a generic prediction of GR. In small in a regime of small redshifts, we are supposed to have a linear relation between velocity and distance. So the main problem when we measure the Hubble constant is distance. This is the most difficult variable, yes, to measure precisely. So if we try to do that locally, yes, in our local volume, we can start with distance measurements around us. These three measurements, these are the most precise direct distance estimations in the local volume. You can see that this is roughly 1% for each of them independently. So here we have parallaxes with new measurements from Gaia satellites. We have precise distance to a large Magellan cloud with detached eclipse binaries. And there's a very special case of observing motion of maser emitting gas around supermassive black hole in this galaxy. And we can solve Keplerian problem fully and measure distance 8 megaparsec. So these are like three basic distance anchors that we can use and try to go to the measurement of the Hubble constant.
So what is delta D? Is the error?
The error, yes, that's the relative error. Yeah. So 1%, that's the relative error. Yeah. And so it should be capital B as well. Yeah. Okay, so if we want to measure the Hubble constant, we have to, of course, propagate distance measurements to a regime of distances where we expect linear relation, yes, between velocity and distance. So all this measurements that I showed you just before, these are very local. So of course there's no expansion in this local volume. So in order to get to really useful distances around 500 megaparsec, we use a technique that is called cosmic distance ladder. So we basically have a sequence of methods which overlap between each other, so that we can propagate local distance anchors up to 500 megaparsec. So the standard way of doing this with the most precise techniques is to use Cepheids, which are pulsating stars, well-known standard candles. With Cepheids we can propagate distances up to 10-20 megaparsec. And then if we go to even further, we need some brighter objects and type-1A supernovae. This is the best what we have. Okay. So if we do that, then so three anchors, Cepheid, type-1A supernovae. So the SHOES team, led by Adam Rees, they combine all these observations, particularly Cepheid, and they get this value of the Hubble constant, 73 plus minus 1. Alternative measurement of the Hubble constant comes from the CMB. So what we do here is basically we are looking at the characteristic scale. It's called distant sound horizon, which is basically leftover of sound waves in primordial plasma. So this is what we can basically calculate precisely from physics. Yes, plasma physics plus GR. From the CMB maps, we can measure basically angular size of this scale on the sky. So if we combine the two, then we have distance. Yes, and then if we want to convert distance to Hubble constant, we have to assume cosmological model. So in this sense, Hubble constant derived from the CMB is cosmology dependent, right? It's a derived parameter. So in practice, what we do, we have this beautiful temperature, power spectrum from Planck, and we fit. It turns out that it's enough to have flat lambda CDM model, 6 parameters. One of the 6 parameters is Hubble constant. So with this flat lambda CDM model, we get really exquisite agreement with the data. There is nothing. There's no need to make any complication here. So flat lambda CDM is fully enough, and the resulting H0 is 67 plus minus 0.5. So if you compare these two values, you can see that there's a large discrepancy, 8% relative difference, 5 sigma significance, and this is what we refer to as the Hubble constant tension. So if we take fully agnostic point of view, there are two possibilities: either systematic errors, terribly underestimated, or there is something wrong with cosmology. Yes, because this value depends basically on our cosmological model. So in order to build, our intuition where to go, and this is systematics or maybe cosmological problem, people were trying to look at alternative measurements of the Hubble constant. Unfortunately, none of them is equally precise in terms of measurement error as as shoes or the CMB base. But it gives you some kind of intuition where to go. Yeah, and now. Normally I say that there are two camps of people, and intuition built, on how we compile these results. Okay, so on the left-hand side, you can see that there are lots of measurements, in the so-called low redshift universe, which tend to cluster around 73, and all CMB based, they are around 67. This plot is typically shown, to try to convince you that okay, there's a problem between early and late universe. Okay. But I can tell you that you can compile this measurements in a different way. If you remove our correlated measurements, terribly imprecise, not updated, and so on, then you end up with this compilation. This is from recent annual report on cosmology by Lahat and Niels, and you can see that actually what is here, a tension between early and late universe. This is basically a tension between shoes and other measurements. Okay. So choose what you want. So here we have systematic, here we have cosmological problem. So every astronomer has her favorite H0. Yep. Yep.
What you're trying to show?
Yes.
What are you trying to show?
So
70 of the red.
Exactly. So if you look at all these measurements around 67. So this is CMB. This is based on clustering of galaxies with BBN prior, so totally independent. It's right on the top, 67.
I see. So
this is
the problem.
Yeah. That's a kind of message of this plot, right? Right. There are also some other alternative measurements. As I mentioned, every astronomer now has her own favorite Hubble constant estimate. I just wanted to show one imaging result. I was involved in this work. So it's a measurement of the Hubble constant based on gamma ray attenuation process. So if you observe the gamma ray source, at high redshift, gamma ray photons interact with extragalactic background-like photons, producing electron-positron pairs, so that you can see attenuation of flux, which you can measure as a cutoff in the spectrum. Yes. So if you do joint analysis of this data, so basically attenuation of the spectrum, extragalactic background light, plus cosmology, because this effect is space with distance, then we get this value 65 with large error, but kind of lower, consistent with Planck. If you combine with VAO and BBN, it goes down to 67. Okay, cosmological anomaly. I'm pretty sure that yes.
For the VAO, though, it is also cosmology dependent or not?
Yes, it depends how you do that. So in this example, you use BBN prior, to calibrate your VAO signal.
So you don't use Planck.
Exactly. So this is CMB independent measurement. So yes. Okay, is it really a cosmological anomaly? I mean, lots of people, believe that this is, cosmological anomaly. We have basically around 300, more than 300 different, proposals, potentially, solutions of the Hubble constant tension. That's a, compilation from a long, lengthy paper by Valentino. I just wanted to point, one important, issue. Why is it really difficult or almost impossible to find a solution which would work, basically? So let's start with this, plot. So what you see here, these are observational constraints on Hubble constant and sun horizon. This is Planck, this little plot, this little contour here, the blue contour. The green contour, this is BAO plus supernovae, and this is Schultz result. So these two bands, green and orange, they are basically cosmology independent. In case of BAO, you have BAO, signal at some redshift, you have to extrapolate to redshift 0. But the shape of expansion history is so well known that it's basically cosmology independent. This green contour. Okay, so now you can see that the only possibility to reconcile these three observations, yes, Schultz, BAO, and Planck, is to shift Planck in this direction, yes, which means that we need to shrink the sound horizon, and at the same time, proportionally, we can increase the right Hubble constant from the CMB. So if you look, at the Friedman equation, how to do that. The only way is basically to put extra energy content in the early universe. That's what GR tells us. Yes, you can do that, in any way you want. The most fashionable, because this is the most flexible actually method, is to introduce early dark energy. Okay, so extra component which pops out somewhere at some moment before coupling, and then decays just before the coupling. Okay, photon decoupling. So that's the mechanism. In principle, with this mechanism, you can shrink the sound horizon and increase the Hubble constant derived from the CMB. But the main problem is here. If you ask the CMB data, if you see any signal for the any evidence for dark energy, that the question is, the answer is no. Okay, so that's a kind of problem here. So when we talk about Hubble constant tension as a cosmological anomaly, I like this quotation from Eric Linder. It really summarizes all these investigations. It is remarkably difficult to shift the Hubble constant from a given value, even in the presence of quite dramatic dynamics at any point in cosmic history, when taking into account cosmology as a whole. So whatever we modify in our standard lambda CDM order, we have to remember that there are other observations, and we cannot destroy very nice fine agreement between lambda CDM and other observations. Okay, so let me switch the gear now and go to type 1a supernovae, which is going to be relevant for the local measurement of the Hubble constant. So type 1a supernova is basically explosion, thermonuclear explosion of white dwarf, which accretes matter from companion star. When it exceeds Chandrasekhar mass, we have explosion, and this is what we observe as type 1a supernova. So this is realistic picture, from our survey, young supernova experiment. You can see here, that type 1a supernova can outshine basically its own host galaxy, right? So since there's a characteristic mass, Chandrasekhar mass for this explosion, we expect that type 1a supernovae should be approximately standard candles. So that's a very old idea. So we can use them to measure distances. That's a historic plot from Permuter et al., where you can see effective magnitude, peak magnitude of type 1a supernova as a function of redshift, and the first evidence of the accelerated expansion of the universe. So what we observe actually these are light curves. So we detect type 1a supernova. We measure flux in different filters as a function of time, and actually these light curves are very easy to interpret, using some empirical models. So the effort of community ended up with a very effective way of compressing information that we see in light curve. Every normal type 1a supernova light curves, in several different bands of electromagnetic spectrum can be represented by 3 parameters only. So that's a empirical model, compressing information to 3 parameters. So what are the parameters? This is peak magnitude, traditionally measured in B band, blue band. Then another parameter is the so-called stretch parameter. It describes the width of the light curve, which you can translate into the decline rate of flux, right? And then the third parameter is color, observed color. So I'm going to talk for the expert. I'm going to talk about salt light curve parameter. So this is C, which is chosen in a way that this is basically observed B minus V color time independent component. Okay. So once I give you these 3 parameters, you know exactly what are the light curves and another way around. Okay. So if you were to use peak magnitude of type 1a supernova to measure distances, then you would see that there is a pretty appreciable scatter, residuals on your plot. Yes. So this tells you that type 1a supernovae, they are not actually standard candles. There is something, there is some intrinsic, effect, that we have to take into account. So already 3 decades ago, people realized that these residuals are well correlated with 2 remaining light curve parameters, which is stretch and color. So there's a simple, prescription, phenomenological prescription. If we subtract this correlation, so linear dependence on stretch and linear dependence on color, we can effectively decrease scatter, on this diagram, and we can get effectively more precise measurement of distance. So you can appreciate, that we can decrease this, intrinsic scatter from 0.3 magnitude to 0.12 magnitude. So this procedure, this correction, double linear correction in stretch parameter and color, this is called trip calibration, and that was the state of the art, model of standardizing supernovae until almost now. Yes, now we are changing a little bit, but that's a kind of fundamental relation. Okay, so there is one problem with this term. So color, observed color of any object, it's always very complicated, because this is basically a sum of intrinsic color and reddening due to dust. In whatever we observe, in space, there is always some cosmic dust along the line of sight. We can easily correct, for the dust effect in the Milky Way, but it's very difficult to correct, for dust in host galaxies, right? So you can say that, assuming this kind of correction, which is linear in observed color, is not physical. Yes, because in practice we have, intrinsic color and reddening, and the response of flux to these 2 things, can be different, right? So now, people are trying, to come up with, more physically motivated, modeling of color correction. It's very simple. So here you can see that, color is basically a sum of intrinsic color and reddening due to dust. We have 2 coefficients, relating the change of the flux or magnitude of supernova in relation to intrinsic color and dust. So this RB coefficient, I'm going to talk about this, in several moments. This is called, the total to selective extinction coefficient. In principle, you can calculate this, theoretically, if you know the dust composition, the distribution of sizes, what sort of dust grains you have. But of course, we don't have this knowledge. Yes, I mean, you observe, any random galaxy, we don't know what is the dust composition there. So typical approach is that, we simply, measure empirically, RB parameter, from observations. The same with that beta EZ. So if you look at this equation, I guess you can easily, realize that, the relation between magnitude, supernova magnitude and color, it's not linear anymore. It's linear only if these two coefficients are exactly equal, yes, which is, the chance of having this situation is very small. Okay, so here's the idea that, if you look, so this is basically, supernova magnitude predicted by this model as a function of observed color. So here, these negative values, these are blue colors. So this is where color is primarily driven by intrinsic color. And when we look at the slope here, this slope, is primarily related to beta SN. And then if we go to the other side, these positive values, these are red supernovae. Red supernovae are primarily driven by dust reddening, and the local slope here is basically related to RB. Yeah. In order to predict this, we need to come up with some kind of reasonable priors for these latent variables, for intrinsic color and for EB minus V. This is a set of priors that is used in basically all works. I'm going to come back, if this is reasonable or not. But it's a, first, the very good, first trial, basically. So Gaussian for intrinsic color and exponential distribution for dust reddening. So the analysis of supernova data, what I show you here, this is basically magnitude of supernova with respect to linearly approximated, color correction. We have some residuals and the function of color. So all what we can do is basically to statistically deconvolve the distribution of observed color into, intrinsic color and reddening. You can measure, the parameters of your prior. Once you have the priors, yes, for your intrinsic color and EB minus V, you can try to measure, the slope of the relation, yes, between the magnitude and intrinsic color and EB minus V. So that's, that's a kind of, schematic, how it works. In practice, you can see that, it's very hard to see any kind of, trend, that you can associate with single value, yes, slope of RB or beta SN. So in practice, we deal with the distribution of these variables. So instead of, single value RB, we have a distribution with some scatter, and this distribution is basically represented by a kind of bundle of slopes, yes, in the red part. Okay. So this is basically, a kind of attempt, to attack this problem, using Bayesian hierarchical models. Yes. Okay. So there is one more complication here. Yes. Yeah.
So you always point the beta one going like down.
Yeah.
So it's not. It's a negative slope.
This is with respect to trip. So this is with respect to slope 3. Yeah.
Okay.
So that would be basically 2 or something here.
Okay.
Yeah. It also depends on supernova compilation and so on, but it's so there is one more complication here. So if we look at similar diagram, so the mean residual magnitude, yes, with respect to linear color correction in different supernova host galaxies, then you can see that there are differences. So this diagram, this plot shows you, what happens, in massive. So this is the blue in massive host galaxies and less massive host galaxies. You can see that there is a clearly a different trend. Yes. By massive, I mean larger than 10 to the 10 solar masses, and this number is simply chosen in a way that we see the largest separation between these two trends. Yes. So now we can say, okay, we can interpret this two slopes that we can see here basically as two different extinction laws. Yes. So extinction law is different in high mass beam and different in low mass beam. Yes. It's a kind of reasonable interpretation. Yes. So this is what researchers behind Pantheon class supernova compilation are trying to pursue, that this separation of the residuals, which is called the mass step, can be interpreted basically as a mass step in RB coefficient So 4 for small mass galaxies and 3 for high mass galaxies. Yeah. Okay. So we have some kind of effective model, yes, of color correction of supernova. We talked about extinction, very physical process. Are we satisfied? Yeah. Now I want to give a little bit of a pinch of bitterness that we are far really from understanding what's going on. So the first one is these are the values of RB we get from supernova analysis. So let's start with this histogram. So this shows you the measurement of RB in the Milky Way. So you can choose many different sight lines, and you can measure this really precisely. Okay. So you can see that one of the values preferred by supernova, RB4, coincides with the peak of the distribution that we see in the Milky Way. That's kind of nice, yes, because if we believe that the Milky Way dust composition is somehow quasi-universal, yes, more or less the same in every galaxy, you would expect exactly the same RB everywhere, yeah. But the problem is with RB lower than 3 and lower than 3, which is preferred by basically a half of supernova, a half of supernova host galaxies, yes? They are not represented here. We don't have any single sight line in the Milky Way which would give you dust composition corresponding to this low value of RB. Okay? We don't know why. We don't know why. And if we try to explain this theoretically, we need to come up with a very special and rare dust configuration in order to get very low RB. If this happens in a half of supernova sight lines for some reason, that's a possibility. Another possibility is that we do something wrong here. Okay. So another problem is that there are some conflicting results. So if we believe that there are two different extinction laws in high mass and low mass host galaxies, then we should see this effect in this analysis where you can see at the mass step in different filters going from optical to infrared. If extinction is the explanation, then the measurements they should follow this great line. Yes. So extinction is higher in optical and much smaller in infrared. From Carnegie supernova project, this measurement is inconsistent with this interpretation. Another analysis of the foundation supernova sample, it's also problematic because they don't find the mass step in extinction as in Pantheon class. So we don't know what's going on. Yes, I mean definitely there is some kind of difference in magnitudes between supernova in host galaxies with large stellar masses versus low stellar masses. We don't know why. Yeah, and I'm not sure if you agree, but there are all options on the table right now. It can be extinction, it can be intrinsic property, or a mixture of all. Yes, we don't understand right now what's the real problem. Okay, so yeah, so with this Bayesian modeling, we made step forward in understanding supernova, but we are still far from understanding really the details. So for example, there is a missing link between intrinsic properties derived from observations and initial conditions of supernova explosions. We don't understand the mass step. We don't understand, what's the physics behind very low extinction coefficient. We don't know why we are supposed to use, the stellar mass as the main variable. Maybe this is just, something, correlated but not a causal variable. So there are lots of questions that are unresolved. We don't understand our priors. I would have to add yes that all results depend strictly on what you assume for the prior of intrinsic color and reddening. If you make any mistake there, something that is not reasonable, then of course our conclusions are also wrong. So I'm a little bit behind what I planned, but I want to mention I want to say a few words about what I about slightly different strategy of looking at supernova standardization, that I and my colleagues are trying to pursue at dark, which is basically two population, Bayesian modeling. So the motivation of doing this is seen here. What you see here, this is basically the distribution of time delay of type 1a supernovae. Time delay is basically a time interval between the formation of a binary system and supernova explosion. I mark, two characteristic, time scales, below 0.5 giga-year and above 0.5 giga-year. In this region, you can clearly see that the distribution decays as T2 minus 1. Okay, so that's an observational result. If you ask theorists, what are the most likely theoretical scenarios for these two regimes of time delays, they would tell you that here, this is a double degenerate binary system, so where we have white dwarfs, and the time scale of shrinking orbit is much larger. So you can suspect that supernovae with really long time delays, these are basically a double degenerate system. Whereas for single degenerate systems, so white dwarf plus normal star, the time interval between formation and explosion can be very short. Type 1a supernovae can explode shortly after star formation period. Okay. If we look at another diagram, this is something very interesting. So this is basically stretch parameter, so the width of the light curve as a function of local specific star formation rate. So this variable tells you basically what is the local stellar activity around supernova. And you can see that there are two main groups of supernovae. So this blue, I call them young. They tend to have high stretch, so slowly declining, and then they tend to be found in active stellar environments. Okay, and if you look at low stretch, you can see that they are typically found in old stellar environments. Okay, so there's a very interesting separation of this supernovae. And clearly, it makes sense to talk about at least two populations, yes, which are associated with two different environments, and perhaps with two different progenitor types. Yes? So this one would be single degenerate, this would be double degenerate. Okay, so maybe this is a good starting. Yes.
Sorry. Explain what is stretch.
Stretch parameter is the width of the light curve. Yeah. So it's well defined, it's literally the width of the light curve. Yes. I should also mention that why we have this kind of dependence between stretch and local environment. It is not known. This is empirical result. Okay, but this is what we see. Okay. So now the main point is that we can think about some kind of maybe a better approach to analyze type 1a supernovae, where we follow this kind of bifurcation diagram. That we have two progenitor channels, single degenerate, double degenerate. They tend to be found in different environments. Perhaps one is more dusty, another less dusty, and so on. Yes, and then eventually what we measure is that three light curve parameters. So in this kind of Bayesian analysis, we can try to do kind of reverse engineering. Yes, starting from observed light curve parameters, we can try to reproduce all these latent variables in both supernova populations. Yeah, and the key idea here is that we can use stretch parameter as a proxy of the local environment. Yes, so high stretch is a young stellar population, low stretch is an old stellar population. Yes. You can clearly see that statistically we can do that in a very nice way, because we can see bimodality in the distribution of stretch. So it's a very nicely defined property. Okay, a little bit about the prior of for dust reddening. So we are trying to pursue a kind of more flexible parameterization, because it makes sense actually to think that there is no one universal prior for reddening, depending on spatial distribution of your type 1a supernovae. If they follow this kind of very extended bulge component of a galaxy, or they are more confined into the disk, you would expect different statistics of column density of dust, and the resulting reddening. So it makes sense actually to check this, yes, to come up with better parameterization. We use this gamma function, which is simple generalization of the exponential function. And let's go to the data and check if there's any difference. Yes, that's the idea. So the idea of modeling is very simple. So you can see that we can see the same linear term in intrinsic color. This is stretch parameter. This is extinction correction. The only difference is that all these latent variables in green, they can come from two different distinct populations associated with young and old supernova populations. Yes. So this is a kind of schematic how it works. You basically look at the distribution of your supernova in the three-dimensional lattice parameter space and constrain your three parameters of your model. And I guess the most interesting result of this analysis is that we do see small, but it's quite significant difference in the distribution of revealing. So you can clearly see that population, the blue population, which is the one that I call young population, yes, prefers more dusty environments. So a little bit higher column density of dust, and this is quite intuitive, yes. So that's a kind of effect of the local environment. Okay, a little bit about the mass step. So in this analysis, we don't use stellar mass as an extra variable, but we can do the following. With our model, we can go back to the data. We can basically type probabilistically every supernova, whether it belongs to young or old stellar population, and we can plot against stellar mass of the host galaxy, and that's the result. So blue, this is young, old, this is old, and you can clearly see that there is a asymmetric distribution, yes, between massive and less massive host galaxies. So which is kind of expected, because if you look at the distribution of stellar age in galaxies across stellar mass, which is shown here, you can see similar effect. So for example, if you start with this plot here, this is stellar mass 10 to the 8. If we go to the right, if we reach 10 to the 10, you can see that we start seeing bimodality. So these are young, these are old, bimodality, and for very massive galaxies, we are dominated by elliptical galaxies, so basically all stellar population. Yes, so there is a nice correspondence, yeah, between this diagram and this diagram. And now what we can do, we can try to basically if our population properties, both for intrinsic and extrinsic properties, they are slightly different, then averaging in stellar mass beams, they will always give you some kind of mass step, yes, a difference, yeah. And if we do that, averaging, then right now we can explain something around 30% of the observed mass step. So maybe this is a kind of way of trying to to understand the mass step just from the basic level of population properties here of supernova. Okay. I have 10 minutes more.
Yeah.
Yeah. Okay. Yeah. So I'd like to talk now about I want to come back to the Hubble constant tension. And I will try to convince you that we see some kind of very worrying anomalies, intrinsic anomalies in the supernova data, and if you try to correct these anomalies, then systematically we can get much lower Hubble constant than the Schuss value. So yeah, so in the cosmic distance ladder we are here. So these are anchors, these are Cepheids, and we are talking about type 1a supernovae right here. Now, what's the motivation? What's the premise? Yes, this is actually encapsulated here in this image. So this mosaic shows you images of calibration galaxies. So these are
That's your work. Your work.
This is actually from Schuss. Yeah, the picture is exactly from the Schuss paper. Yeah.
But they are trying to reduce the constant.
I would try to, yeah, I'm working on this. Yeah. So I will get to this point. Okay. Yeah. So now I'm starting with kind of motivation. Yes. Why we can expect, possible systematic effects in the supernova sector. Yeah. So the starting point is this image. So these are calibration galaxies. So these are galaxies where we observe Cepheids and type 1a supernovae. Yeah. You can see that this is not a statistical representation of the universe. This is a completely biased sample, late type star-forming spirals. Yes. Just because we can observe Cepheids only in this kind of type of galaxies. Yes. So we start with a biased sample, and you can ask yourself, it's biased actually also in respect to supernova. So this is the plot that I showed you. So basically stretch versus local specific star formation rate. And this is the distribution of stretch parameter in the calibration sample. You can see that it coincides with this blue cloud. Not with the red, with the blue. So just by selecting these galaxies, we preferentially select young type 1a supernova. Yes. So now you can ask yourself, okay, there are some latent variables, physical variables, which are related to host properties. Yes. If our host properties are different in the calibration than in the Hubble flow, then maybe our calibration supernova, they can be shifted relative to the Hubble flow. Yeah, and you can, that would be basically, a bias in the measurement of the Hubble constant. Yeah, this is at least, a hypothesis that we have to check. Yes, if there is no any systematic difference triggered by the selection of by the selection effect. Okay, so the first, warning signal that we got, it was in the analysis of data from Schu's team 2016. So this is where the Hubble constant grew to 4.2 sigma. It was already, quite strong. What you see here, this is a difference between supernova corrected magnitude and distance modulus from Cepheids in the calibration galaxies. Yes. So the model that we use to calculate, corrected magnitude of supernova is trained on the Hubble flow, and then it is extrapolated to the calibration. Yes. If there is no any mistake in this extrapolation, then we shouldn't see any correlation between residuals here and supernova color. But you can see that there is something wrong here. Yes, I mean, blue supernovae, they are much below. Red supernova are much above. If you play with statistics, fitting different slope of color correction in this, then you can see that there is a basically 3 sigma intrinsic anomaly on this diagram in 4.2 sigma measurement. Yes, so that's something worrying. Then if you try to measure Hubble constant from this data, this is a little bit problematic because in the previous version in that version of Schu's data, they were using simple trip model, so linear relation in color. So basically your Hubble constant measurement would depend basically on a reference color that you use to match magnitude color relation in the calibration and Hubble flow. Yes, if the slopes of these two relations are exactly the same, then it's a well-defined problem. These are two parallel lines. If they're not parallel, then you have to define reference color, right? Simple geometry. So this shows you the resulting Hubble constant as a function of reference color, and for these blue colors, which are physically blue, these are physically blue supernovae. You can clearly see that we can go down to 60. 70, 60, 68, Planck value basically of the Hubble constant. Yes. So what's so special about these blue colors? The blue supernovae, they are the least affected by dust extinction. Okay. So this brings you some kind of intuition that okay, if the difference in this color correction between calibration and Hubble flow that we see in the data is due to difference in extinction, then a simple way to mitigate this problem is to look, at H0, for blue supernovae, and you can go down, to the Planck value. Yeah, so that's something telling. Then you can also do like a full Bayesian analysis where you split color into intrinsic, reddening, and so on. And that was a part of of bachelor project of my student who defended successfully 2 days ago. And unsurprisingly, you get 68 plus minus 1.8.
But so for this, you had two populations
Yeah,
for
that's
the
a single
calibration
population.
and for the Hubble flow.
Yeah. So you basically you allow extinction parameter to be different in calibration sample and Hubble flow. Yeah, that's the key assumption. Yeah. Okay, so then we had new data from the shoes. So in 2022, they published new measurement of the Hubble constant, which is in 5 sigma tension with Planck. There are some new things in their data. There are 2 more calibrators. So calibration galaxies, more supernovae, and what is really important here that the supernova sample employs a model of extinction with the mass step trained on hierarchical data. That's the mass step that I showed you a few slides ago. Yes. So this model is trained on totally different data, hierarchical supernova, and then it is this is employed extrapolated to calibration galaxies. Yeah. The question is can we do that? Yeah, it's a empirical question. If all is fine, then we shouldn't see any abnormal residuals. But the problem is that we do see. If you look at these red points, these are supernovae in massive host galaxies where we apply very low extinction correction. You can see that they are systematically below. Okay, we can measure the strength, statistical strength of this trend. It's slightly above 2 sigma, but this is kind of problematic. Yes, I mean if we claim that we have 5 sigma signal with 2 sigma intrinsic problem, then it's not good, right? Okay, so on the right hand side right now I'm showing you extinction correction that they apply to calibration galaxies. Yes, and again I repeat that this is a result of training a model at high redshift supernovae and then extrapolated to calibration. Yeah, you can see that the difference between the 2 mass beams, so low mass and high mass host galaxies. This is basically the scale of the Hubble constant tension, 0.15 magnitude. If we make a mistake in extinction model here, then it's very easy to shift by an appreciable fraction of the Hubble constant tension, right? 0.15 magnitude. That's a lot. And you can see that you can associate that. You can see that there's a correspondence. This red supernova in high mass galaxies. They correspond to this extinction correction in which we assume very low RB value. Okay, so we have a problem. From the point of view of statistics, we have some unaccounted residuals. There is some intrinsic anomaly. So we try to come up with simple remedy, minimalistic modification of how we correct extinction in the calibration sample. And the model is very simple. So we assume simply Milky Way-like distribution. Okay, because these galaxies, these are Milky Way analogs. So everybody who works on dust models, they will tell you that the most likely dust composition is exactly the same like in the Milky Way. And the most likely expected RB value is 4.3. Why not to assume? The second motivation is that this is the extinction that is assumed for correcting extinction in Cepheids. Okay, so in the original analysis of the shoes data, you assume RB 4.3 for Cepheids and RB 3 for supernovae, despite the fact that they are in the same galaxies. Yeah. So the question is, what's the physical process? Yes, I mean that you have, 2 different, extinction corrections for Cepheids and for supernovae. So this proposal, we solve this problem. It's easy Milky Way, the most expected extinction model. The other thing that we have to tune a little bit is the distribution of reddening in order to get really nice fit. This blue line, this is what we need, and you can see that it coincides with the distribution of reddening that we got for young supernovae population. which is again expected in these galaxies. So there's a lot of nice correspondences. So so if you apply this model, it's a very complicated, because you have to correct all these biases, correct covariance matrices, in Cantillon class. But if you do the job, you can see that this model of this new model of extinction works better, and the Hubble constant that we get is this 70.5 plus minus 1. Okay. So qualitatively speaking, in the new data from SHUS, we see exactly the same problem, that extinction in the calibration supernovae seems to be underestimated. If you correct for this effect, then the H0 value goes down automatically. Just 2 minutes more, okay? Sure. So this is the kind of continuation of this project. Now we are trying to do that, in the full Bayesian framework, where you basically, the idea is that all intrinsic properties, they are simultaneously constrained by calibration galaxies, and Hubble flow. But you can allow for some differences in extrinsic properties. Like, you can ask yourself, whether, there's any difference in extinction, calibration versus Hubble flow, and so on, yeah? So that's the kind of, nice framework to explore what are the possibilities. And I want to finish, with this plot. So this plot shows you basically, the right Hubble constant value and the mean extinction that you measure in the calibration galaxies independently, yeah? So if we focus on this gray contour, then you can see that there is a nice degeneracy, low RB and high H0, and high RB and low value of the Hubble constant. So
that's for all of the galaxy calibration galaxies.
Yeah, this is just for the calibration galaxies. Yeah, I have lots of very complicated extended corner plots you can explore together. Yeah, but this is actually the most essential result. So it tells you that calibration data allows you to choose RB in this pretty large range of values. Yes, including the value 4.3. That is what is a natural choice. Yes, for Milky Way analogs, and so on. Yeah. So if you are, of course, if you use, 4.3 as a prior, then you get, H0 770, and then, depending, how you treat, intrinsic scatter, there's some kind of technicalities, the resulting H0 value is 72 plus minus 2, or 70.2 plus minus 1.5. So general trend is, is the following, that, if we consider, models which share the same philosophy of modeling the data, that you train your model on the Hubble flow, simple model, complex model, whatever, but you train on the Hubble flow, and then you apply to the calibration sample. So you assume basically universality of what you get from the Hubble flow, then you are systematically, at 73. If you break this universality, so you allow, for extinction, for example, parameter to be independent, and different in calibration sample, you can easily go to the Hubble constant 70. Okay, so that's work in progress. These are all preliminary results. I'm exploring all these Bayesian models, but to me, there's a very interesting direction that is really not explored and not fully appreciated, and it's really super important in the context of understanding the Hubble constant tension. This is just a historical remark. I'm sure if you saw this these are measurements of the Hubble constant as a function of time. So we start with Hubble, who measured actually 600 kilometers per second per megaparsec. Then people realized that to mix two different populations of Cepheids, if you correct for that, then it goes down to 200. Then we had a period of time where there were two very influential astronomers, Sandage and de Vaucouleurs, and they disagree by 50. So one got used to get 50, another 100 kilometers per second per megaparsec. Eventually, the result converged to 70, and now we have just 6. larger supernova process. So, the question is, is it, the same story again, but, with different scale of systematic error? Yeah. That's a question. So, yeah, so these are, this is kind of, summary. I guess, I'm going to leave you with bullet points, and sorry for, talking a bit too long. Thank you for your patience.
We have time for a couple of questions.
Can you make Greece agree with you?
We are in a phase of constructive discussion now, because it started a year ago with a little bit of emotional reaction. Yes. I think that I don't want to speak for him, but my impression is that he takes this as a serious possibility. There is no any question, if we have these anomalies, that's a fact. Yes, I mean we see this uncounted residuals. Yes, the question is how to interpret this. So I hope that we are in a kind of in the phase of getting into some kind of constructive dialogue, and he's quite open to explore this. Yeah. I don't want to say, I want to convey the picture that we are done. This is the beginning. Yes, because if we want to convince, for example, our community that for some reason in this galaxies there's a higher extinction, we need to know extra observational arguments. We need to understand theoretically why is it so, in terms of dust formation, dust composition, and so on. So there's lots of work ahead, but this is really a possible scenario. Yeah. Yeah, dust is kind of infamous for misleading. Yes, as in terms of cosmological interpretations of data. I just recall bicep, yes, story. So it was just interpreted as signature of primordial gravitational waves. It turned out that was Milky Way dust. Yeah. I don't want to say that any strange cosmological signal is caused by dust, but it looks like this is again the same player in the game. Yeah. Yeah.
So basically building a representative good sample at low redshift of the calibration, so galaxies that have Cepheids and Taiwanese supernovae that correspond to the high redshift is going to be very hard, I think, right, in the next future. So maybe what we can do is at high redshift, find a sample that is consistent with the calibration sample, right?
Yes.
And then we can build a model that is consistent in all of the galaxies and try to. So what would be those galaxies, or do you have an idea how to perceive?
Yeah, that's a great question. Yes. So if we so the idea here is if we select in the Hubble clock in exactly the same way, like in the calibration, then the problem should disappear. Yeah. We cannot do that in exactly the same way how we select in the calibration, because our selection is based on observability of Cepheids. Yeah, I cannot go to redshift 0.1 and ask, okay, can I see Cepheid? Yeah, and so on. So we have to use some proxies. Yeah, and now the question is, if any proxy you come up with, is precise enough to do this matching or not. Yeah, and we can experiment. With that. Yeah, so we can look at morphological types. We can look at star formation history. That they should match, yes, and so on. Yeah, that's a reasonable direction. Yeah. Yeah.
There was another question.
I'm not sure I understood. Did you say that the systematics from the two first steps of the algorithm are not as important as the ones?
From the first two run, like Cepheids and I think that there was so first of all we have three different distance anchors. starting, at the zero level of this ladder, yes? And for each of them, you get consistently the same Hubble constant value, which I take as a kind of, evidence that, there's no problem with the zero level of the distance ladder, yes? With Cepheids, there were lots of tests, Adam Rees, performed lots of tests, with JWST, they are checking for, effects of, crowding, for example. If you have a poor resolution of your telescope, then you can accidentally see some other stars around your Cepheids, yes, also your flux will be screwed up, yes. So they are all checking all these effects, and it seems that, this is all stable. There is no any big systematic, issue. That's my understanding, yeah, with Cepheids, yeah. But somehow, we believe, maybe not I, but a big part of the community believes that type 1a supernovae are fully reliable just because we discovered cosmic acceleration, yes. But this experiment is very different because in the discovery of dark energy we don't play with selection of host galaxies. We have exactly the same selection at different redshifts and so on. Here we deal with this terrible selection effect, and we don't understand what are the implications for the Hubble constant. So it's a very different experiment than dark energy. So there's no point, to say that type 1a's are fully reliable. Yeah, we don't have physically motivated models of standardizations, all these problems that I talked about. So yeah.
Do you think the solution to the short tension is coming mostly from low redshift correction?
Low redshift correction. I wouldn't say so you want to interpret, for example, this different extinction as a kind of new physics, or
just in comparison.
Okay. I see. Yeah. So there are some ideas where proposing that something strange happens at very low redshift. Yeah, like 0.03. Yes. Including, for example, a rapid change in the gravitational constant. Yes. That's a kind of the most exotic example. Yes. I would be cautious. Yeah, because that's an extinction. This is there's no exotic physics. It's a very solid physics, but it's very difficult to constrain it, observationally. So if I were to invest my money in what direction, I would say yeah, let's investigate extinction and dust. Yeah.
If you enjoyed the video, like and subscribe.